So let's see, there we go. Okay, so, again, we are talking about binomial distribution over here. So when we're talking about finding the mean, variance, and standard deviation, they're basically saying you can use the formulas that we found or that we talked about in the previous section, section 5.2, but you can also use these formulas, these formulas here, which are, again, you can kind of think of them as a shortcut method. So when we're talking about the mean, you're actually just taking your, there we go. So you can basically, to find your mean, you can take the n, multiply with p, so n times p. When we're talking about variance, that's again n times p, but now you're also multiplying the q value. So again, remember, n is the number of trials we have, p is of course the probability of the success, and q would be the probability of the failure. And then of course, same thing, if you take a square root on the variance, you get your standard deviation. So you can use the formulas from the previous section, or you can use these formulas here from this section here. So let's just take a look at a couple examples. This one is talking about tossing a coin 4 times and then finding the mean, variance, and standard deviation for the number of heads that we can obtain. So of course, in this case, we're tossing the coin 4 times, so our n value equals 4. We know the probability of getting a head is 1/2, and a probability of getting a tail is also 1/2. So when you're talking about the mean, it's basically going to be n times p, which is 4 times 1/2, which will of course come out to be 2. For the standard deviation or variance, actually, you're taking the 4 and the 1/2, which was basically the answer from the mean, and just multiplying it with the q value. So that's going to be 1/2. So technically you're multiplying 4 with 1/4, which would of course just end up giving us 1 as the answer, and then take a square root of 1, which would give us our standard deviation. So in this case, we are basically saying that the mean when you are tossing this coin 4 times will be, out of those 4 times, you can end up getting 2 heads as a mean, and that gives us a variance of 1 and also a standard deviation of 1. So very, very, straightforward as far as the calculations go. They are saying, for this example 8 that we just talked about, when the 4 coins are tossed many, many times, the average number of heads that appear is 2. So, basically we are saying, if you're going to be taking these 4 coins and tossing it, and you do this, repeat this experiment several times, basically that average will start getting closer and closer to 2. And, of course, we saw that the standard deviation would also come out to be 1. Now, obviously, we're not performing the experiment. We're just talking in terms of, theoretically, what these values would come out to be. So, if you were to actually do this experiment, your answers, obviously can be a little bit different, since we're looking at the theoretical values, and the actual values would come out to be a little bit different. Okay, so example 9 here, we're looking at an 8-sided die, which means, your numbers would go from 1 through 8. They are saying this 8-sided die is rolled 560 times. So what could be the mean, variance, and standard deviation of the number of 7s that will be rolled? So, obviously they're telling us that the die is rolled 560 times, so that's going to be the n value. But now specifically they're asking the mean, variance, and standard deviation for the number of 7s. So of course we know the probability of getting a 7 out of those 8 different faces is going to be 1 out of 8, which means the probability of failure, which means not getting a 7, is going to be all the other faces, which of course comes out to be 7 out of 8, right? So again, multiplying n times p gives us the mean, which is 560 times 1/8, and that's a mean of 70. So we're basically saying out of the 560 rolls that we are going to be doing, we're saying the mean of number sevens is going to be 70. So basically 70 times we can kind of expect to see, number 7 show up. So that's going to be your mean value or the average. For your variance, you take the n times p times q. So basically 70 can be multiplied with that 7/8, which as you can see ends up giving us 61.25, and then taking a square root on that gives us our standard deviation of approximately 7.826. So with a mean of 70, and we are saying a standard deviation will come out to be 7.826 times. So, of course, then that tells you that if the average is 70, you can get, a standard deviation of 1 or 2. You can see what kind of rolls that will be, which will end up giving you the number 7 when you roll this 8-sided die. Just another example over here is with the source book of criminal justice statistics states that 65% of Americans favor sentencing drunk drivers to jail, even if they have not caused an accident. So that's your probability over there. And then they're saying if a random number of 1,000 individuals is selected, find the mean variance and standard deviation of the people who feel this way. So obviously, we're selecting a sample size of 1,000 people, so that's going to be our n value. They're telling us the probability is that 65% of Americans favor sentencing drunk drivers to jail, so that's your probability. 1,000 multiplied by 0.65, of course, gives us 650. And with that 650, if you multiply the probability of failure, that's our Q value, that gives us the variance. So of course, if 65% feel that drunk drivers should be, sentenced to jail, then of course 35% would feel the other way, which means they would not be in the favor of sentencing. So that's where this 35.35 is coming from. Multiply that together and you end up getting a variance of 227.5. Taking a square root of that, of course, gives us a standard deviation of 15.083. So we're basically saying from this sample of 1,000 individuals, 650 would be the mean, and we are saying the standard deviation would be 15.083, and of course we have our variance in there. So you can see again, it's just a matter of multiplying the number of trials with your probability for success and or failure, depending on what calculations we are doing. So I've got a couple examples from our textbook over here. Let's take a look at those. So how about number 22 over here? So this one here, we've got, it has been reported that 83% of federal government employees use email. If a sample of 200 federal government employees is selected, find the mean variance and standard deviation of the number who use email. So let's go ahead and see what this would come out looking like. Okay, so can you tell me what our N, P, and Q values are going to be? Okay, Alexander, so they are telling us we have a sample of 200 federal government employees. So very good, 200 would be our sample size, or the N value. Probability would be 83%, because they are telling us, to find the mean variance and standard deviation for the employees who use email. So that's the 83%, so 0.83, and then subtract the 0.83 from 1, and you would get 0.17 as your probability of the failure. Alrighty, very good, very nice. So now let's talk about the mean. variance and standard deviation. So let me see what these values come out to be. So remember, it's n times p for this one, n times p times q over here, and then square root of n times p times q. So what would that mean come out to be? Okay, let's see, Alexander, you've got 166 for the mean. Okay, hold on a second. That would actually be 200 multiplied by 0.83, and that's 166, okay? And then for the variance, you've got 28.2, okay? So the raw answer is actually 28.22, and we actually don't know what our raw value is going to be over here. So I guess I'm going to leave my decimals as it is and then just take a square root on that number. And then of course we would have our standard deviation. And looks like Alexander, you've got 5.3 on that. So the raw answer is coming out to be 5.3122, and you know, it keeps going. So they didn't really tell us anything, about the rounding rules here. Not really. Jasmine, you got the same answer? Okay, very nice. Okay, so I guess I'm gonna leave it at 5.312, but you know, hopefully in Connect Math, you should be seeing, I would hope, rounding rules, how far they want you to round this, because you know, normally the rounding rule is you do one decimal place more than what the outcomes are, but they're not really giving us any outcomes here. They're just kind of giving us the probability and you know how many trials we are doing. Okay, so at least this kind of gives us a little bit of an idea of how these calculations would work out. Okay, I've got one more example that I wanted us to look at. How about number 24 over here? So 85% of Americans favor spending government money to develop alternative sources of fuel for automobiles. For a random sample of 120 Americans, find the mean, variance, and standard deviation for the number who favor government spending for alternative fuels. So let me see what you come up with for this guy. So again, what's the N, P, and Q values here? Alrighty, Jasmine, you've got 120 for N because they're telling us it's a random sample of 120 Americans. Very good. For the number of people who favor government spending for alternative fuels, they're telling us it is 85%, so 0.85. So of course that means 1 minus 0.85, of course will end up giving us the 0.15 as the value for Q. Alrighty, very nice. So go ahead. Now that you have these values, please tell me what our mean, variance, and standard deviation will end up looking like. Okay, let's see, Alexander, you've got 120 multiplied by 0.85. Jasmine, you got the same. Okay, so 102 for the mean. And then, of course, you are just taking that 102 from the mean and multiplying that with our 0.15, which would give you the variance. And let's see, you got 15.3. Okay. And then, of course, the last one is where you just take the square root on 15.3 to get your standard deviation. And let's see, you've got the raw answer comes out to be 3.91152, and of course keeps going. So just kind of sticking with that 3 decimal place, you are getting 3.91, and that 5 makes it go up to 2. Okay, very good, very nice. And that's what you guys had, so that works out. So again, just, got to be a little bit careful of just making sure you're identifying the right values. And then, as I told you, the calculations are pretty straightforward. I've got a couple more examples. I just wanted to make sure you guys would be comfortable working through. So let's see what answers you can come up with. Let's take a look at this guy over here, number 26. In a survey, 63% of Americans said they own an answering machine. If 14 Americans are selected at random, find the probability that exactly 9 own an answering machine. So what kind of calculation would you use for this example here? So obviously you can see they're not asking us to find the mean, variance, and standard deviation here. They're saying if 14 are selected at random, what's the probability that exactly 9 would own an answering machine? Yeah, very nice, Alexander. Exactly, you need to use the binomial formula in this case. So remember your binomial formula. Let me show you that really quickly. So right here, this one is what you are looking at for your binomial formula. So let's try and use this in our example that we have. So what is going to be our given values over here? What can you identify from this example? So in the binomial formula, again, if you wanted to look for the binomial formula, you need the n, the x, the p, and the q value. So go ahead and identify all four of those values, and what will that be? N, x, p, and q. Okay, let's see. We've got n equals 14, Alexander. P equals 63%, so 0.63. They own their own answering machine. X would equal 9, and Q would be, of course, 1 minus 0.63, which is 0.37. Alrighty, very nice. So now that you have all of these values, you can go ahead and plug it into this formula. So let's see what that comes out to be then. Okay, so n is 14. X would be, since they're telling us it's exactly 9, X would be equal to 9. Probability of success is 0.63. Probability of failure will become 0.37. So you are looking at exactly 9. So that's 14 factorial divided by 14 minus 9 factorial, 9 factorial, and then multiplied by 0.63 raised to the power of 9, and 0.37, which would be raised to the power of 14 minus 9. Okay, so go ahead, do your calculations, and let me see what you come up with. Okay, so remember, this is a probability, so use your rounding rules for probability in this case. Okay, so what did you come up with? Okay, so remember, Alexander, with probabilities, we always round it to 3 decimal places. Okay, not a problem. Alrighty, very good. Yes, it comes out to be, and again, I'll give you the raw answer over here, 21703, and then, of course, it's going to keep going, 8929. So when you're rounding this to 3 decimal places, you can see, since we have a 0 after that 7, you are going to round it to 217, as your answer. Kimberly, you got the same thing already. Very nice. Very good. So that would be a probability. So basically, we are saying if out of 14 randomly chosen people, if you want exactly nine, who are going to own an answering machine, we are saying that's a very low probability of only 0.217, or approximately 21.7%. So yeah, I mean, you're not probably going to find a whole lot of people, if you're choosing 14 and you want to know that exactly nine out of those 14 would have an answering machine. That's a pretty unlikely scenario when we look at this probability value over here. Alrighty, very nice. One last example from this section before we move on to chapter 6. So let's go ahead and take a look at number 30 over here. And this one is talking about, in a recent year, 13% of businesses have eliminated jobs. If 5 businesses are selected at random, find the probability that at least 3 have eliminated jobs during that year. So again, what kind of calculation would we need to use in this case? So in a recent year, 13% of the businesses have eliminated jobs. If 5 are selected at random, what's the probability that at least 3 of them would have eliminated jobs during that year? So when we're talking about at least 3, what kind of calculation would we need to do here? Because remember, we have looked at example like this yesterday when they talk about at least or at most, or fewer than. We just looked at an example for exactly 9. So how would you set up this problem? So the first thing that should jump out is, again, the 13% should tell you you have to use the binomial probability formula, right? Because 13% is not going to be in the table. So we won't be able to use the table over here. Now for the at least 3, what probabilities will you need to find to answer that question? Probability of none. Alexander, you said finding probabilities of 3, 4, and 5. Okay. So yeah, if you are selecting 5 businesses at random, and we are talking about at least 3 of them, we are saying at the minimum 3 of them would have eliminated jobs, but that also means more than 3, right? So it can be 3 businesses, 4 businesses, or 5 businesses. So they are actually asking us for X being greater than or equal to 3 when they say at least 3. Now, what kind of N, P, and Q values are you looking at here? Okay, Jaslyn, very good. I'm glad. So your N, P, and Q values. Okay, yeah, we are choosing 5 businesses at random, so N would be 5. They're telling us 13% of the businesses eliminated jobs, so that's your probability of success, 0.13. So subtract that from 1. Kimberly, very good. Yeah, Jasmine. So Q, in this case, of course, that means 87 of the percent of the businesses actually did not eliminate jobs, right? So 0.87. All right. So in this case, like Alexander said, you have to do this for 3, 4, and 5. So that actually means you are looking at finding the probability for x equals 3, finding the probability for x equals 4, finding the probability for x equals 5, and then we would have to add all of them up together. So since we are using the binomial probability formula, that would be 5 factorial, then 5 minus 3 factorial, 3 factorial, then multiply this by 0.13 raised to the power of 3, and 0.87, which would be raised to the power of 5 minus 3, which is of course technically 2. So go ahead, find each of these values. Let me see what you come up with. So use the same rounding rule, round each one of your individual probabilities to 3 decimal places, and then we'll add them together. Okay, let's see, Alexander, you've got, so let's see, this one, the probability for 3 is 0.01662. So rounding it to 3 decimal places, you would have 0. Oh, sorry, I missed a 0 in there. That should be 0.017. Okay, so that one looks good. And then you've got 0.001 for that second one. Okay. So let's see, that raw number is coming out to be 0.00124. So rounding it to 3 decimal places, you are getting 0.001. Okay, so that one also looks good. And then the last one, we are doing, of course, 5 out of 5. So that's going to be, raw score is coming out to be, let's see, 1, 2, 3, 4. And then we've got 3, 7, 1, 2, 9. So in this case, where you have a bunch of zeros after the decimal place, remember you always round it to the first non-zero digit. So this one actually rounds to 0.0000, and that 37 will basically go up to a 4. Alrighty, very nice, Alexander, nicely done. So you are now going to add all three of these numbers to get that final probability for at least 3. So you're taking 0.017, adding that with 0.001, and then of course adding that with 0.00004. And what is that total coming out to be? 0.018, okay? So what's going to happen is, of course, you are going to have, more decimal places because of that 0.00004. So when you just add these numbers up together, you are going to end up with 0.01804. And then when you round it to 3 decimal places, you would, of course, stop right here, and you end up getting 0.018 as your final answer for at least 3 out of the 5 businesses would have eliminated jobs in that given year that you're looking at. So just be careful. Most of these calculations are about how they are phrasing the question to you. Are they saying exactly 3, at least 3? Remember, some of them will say at the most. And I know we had looked at an example like that yesterday. So just be careful about how they are stating their question. And then, of course, you also have these examples on the mean variance and standard deviation. I'm not seeing an example over here. Okay, right here. So you can see how they have in number 13 exactly 3, at most 4, at least 3, fewer than 2. So be careful about how they phrase that question to you. Okay, so this was our the last couple examples that I wanted us to look at in section 5.3. So before I move on to the next chapter, did you guys have any questions about chapter 5? You guys are okay? Alrighty, very good. So let's move on to chapter 6 then. And this is where we're getting into, again, we're still talking about probability distribution, but remember chapter 5 was about the discrete probability distribution, where we're talking about the binomial distribution. So here in chapter 6, we're talking about probability distribution, but this time for continuous variables. And so, of course, this is where we bring in the idea of the normal distribution. So, like I said, here we are focusing on the continuous. Discrete is what we did in chapter 5. So again, keep in mind when we're talking about discrete variables, those are the ones that you count. So they will take that specific number as its value. But when we're talking about continuous variables, we are saying that your continuous variable can assume all values, which would be between any two given values for the variable. So, you can also have decimal or fraction values in a continuous variable, because they would fall, in between two given values. So just as examples of continuous variables, you can think of height. They're talking about adult men, but of course height for any individual. You can talk about temperature, so body temperature of rats. We can look at the cholesterol level for adults. So, any of these kind of measurements would be considered as continuous variables. Now, keep in mind, for many of these continuous variables, their distributions end up having a bell-shaped kind of distribution. And these are called approximately normally distributed variables. And a best way to kind of think about what these examples would end up looking like, they have a really good illustration over here. So they're saying, for example, if a researcher selects a random sample of 100 adult women and they measure their heights, construct a histogram. So basically your histogram would end up looking like something like this graph A over here. So you can kind of see that histogram. It's got somewhat of a relatively bell-shaped distribution to it. But the idea is if you increase the sample size, so instead of 100 adult women, let's say you went with maybe 1,000 adult women. So if you increase the sample size and decrease the width for your classes, so remember how we define classes, when we are creating histograms. So if you start decreasing that width of your classes, then you will see our, bars on the histogram will start becoming narrower. They're not going to be as wide because we are decreasing the class width. And of course, we are also increasing our sample size. So you will again kind of see how that histogram will change a little bit. And you can kind of see that in graph B over here. So again, you can see it's starting to get more of that bell-shaped curve as we increase our sample size and decrease the class width. If we continue doing this, we increase our sample size again and decrease the class width even further, then your histogram will end up looking like graph C over here. And you can see how, again, it's getting a more defined bell-shaped curve. So the idea is, as you keep increasing your sample size, and start making those class widths smaller and smaller, you are actually going to start seeing a more of that bell-shaped curve. It's going to start getting more of that smoother look. And the idea is, if it were possible for us to measure, all the adult females in the US and get their heights, and if we were to plot them, they would actually end up getting this more smooth curve over here that you're seeing in graph D. And this is actually what we call as our normal distribution curve, because now you can exactly see what that bell shape of our distribution ends up looking like. So this is what we call as the normal distribution curve. Sometimes you will, of course, see it being called as the bell curve, or in some textbooks, they like to call this the Gaussian distribution curve, because, Carl Friedrich Gauss was actually the one who came up with the equation for this normal distribution. So a lot of times you will see it referred to as the Gaussian curve. But that's basically the idea behind these normal curves, or these bell-shaped curves, is if we were able to take our entire population, so like in this example, we're talking about all the adult women in the United States, and actually take their heights and plot it, you should see this distribution curve over here. Now, again, keep in mind that this is a theoretical distribution. So obviously, if we were to try and graph this with, if it were possible for us to have all the adult female heights in the US, it may look a little bit different, but you should still kind of see that general shape. But we're obviously basing this more on a theoretical distribution than an actual observation kind of distribution. So they are saying basically this normal distribution can be used with many different types of variables, because a lot of variables will show the same behavior as what we're seeing with heights over here. And they are saying basically the deviations for a normal distribution are very small. And so that's why a lot of different types of variables can be used with this normal bell-shaped curve over here. So we're definitely going to get quite a bit of detailed work done with this normal distribution, how we can use it with applications. But we are also going to talk about the central limit theorem, which is an important aspect of the normal distribution. So we'll look at that. And then we are also actually going to look at how you can use the normal distribution to basically do an approximation for other types of distribution. So mainly we will be looking at how we can use a normal distribution to help us approximate a binomial distribution. And the one thing we have to kind of keep in mind, binomial distribution, remember, is a discrete distribution, whereas the normal is a continuous distribution. So, they're talking about making a little bit of a correction when we are kind of making these approximations. So we'll be talking about that towards the end of this chapter. So we have done, little snippets of normal distribution discussions before. Remember when we talked about finding the standard score in chapter 3, when we were looking at measures of position, we had talked about, the standard score then. We also talked about the empirical rule when we were talking about the Chebyshev theorem. So, we've kind of introduced a little bit of that aspect of normal distribution in the previous chapters, but, obviously we're getting more in depth over here. So just as a background, we're talking about how you can have equations that represent curves in mathematics. So, you have the equation of a circle over here, x squared plus y squared equals r squared, where that value of r is basically going to give us the radius of the circle. Now, this concept of a circle can be used on any circular object. So we're talking about, you can use the circle to represent a wheel or even a gear. And, obviously when you are talking about this in terms of practicality, a wheel may not show all the properties of a circle because it may not be a perfectly round circle, but, we of course still use the properties of a circle. You can talk about, if you're especially looking at a wheel, you can talk about how to find its area, velocity, and acceleration just based on this idea that a wheel is a circle. So that's the same thing what we are doing here. Since we are talking about using a normal distribution curve, we are going to look at many different variables that would show that general shape of the normal distribution curve. But again, remember, it may not be exactly the same. So it will be more of an approximate calculation than it would be an exact calculation, okay? So just as a definition, we are saying if a random variable has a probability distribution whose graph is continuous, bell-shaped, and symmetric, it is called a normal distribution. And then, of course, the graph itself would be called a normal distribution curve. Now, you actually do have an equation that can be used for the normal distribution, but, we typically do not like using these equations. And you can kind of see it's a little bit of a involved calculation here because you have that natural number e, which is raised to the exponent of, as you can see, negative quantity of x minus mu squared divided by 2 times the variance. And then that whole thing is being divided by standard deviation, sigma, multiplied with square root of 2 pi. So obviously, we don't want to keep messing around with this equation. So we are actually going to stick to tables. Now they're talking about technology, and technology would be, if you're using a computer program or a program on your calculator to help simplify. But, we are going to be sticking with tables over here. So again, you should see this table in your D2L Flash shell, but I'll go ahead and send you the file just to make sure you guys have this. Because again, this table will come in really handy when we are trying to do our calculations over here. So it's 2 pages to this table that we'll be looking at. And one of the things that we actually are more interested in when we are using these normal distribution calculations is we're actually more interested in that area which is under the normal distribution curve. We are not so much interested as what the values on the y-axis are going to be. So you will notice a lot of times when we draw these normal distribution curves, we just draw that horizontal x-axis, but we do not normally draw the y-axis because we're not really looking at the values on the y-axis. Like I said, we are more interested in that area which will be under the normal distribution curve that we're interested in. And that's exactly what these tables also do, is they actually tell us what that area is going to be, but in terms of probability. Alrighty, so keep in mind, when we are working through these normal distribution curves, we are interested in what the mean of our data set is going to be and what the standard deviation is going to be, because these two values of mean and standard deviation are actually going to help us decide what kind of shape and position our normal distribution curve is going to have. You know, they are all going to be continuous, they're all going to be bell shaped, they will all be symmetric, but you know, depending on what the mean and standard deviation is, because remember, standard deviation tells us what the dispersion or variation of our data set is going to be. So that will be reflected in your normal distribution curve, because that will tell you how spread out your curve is going to be based on, you know, where the mean is at and what your standard deviation is going to be. So each curve, each variable will have its own mean, its own standard deviation, and of course its own curve to represent that data set. So just as a comparison over here, this first one here, we're looking at a mean value of 0 and a standard deviation of 1. So that's actually going to be this curve. I don't know what the color looks like to you. It kind of looks brownish something to me. So the brown colored curve is where your mean is at 0 and standard deviation is at 1. If you look at the curve, which is kind of in that bluish color, that has a mean of 0, but this time the standard deviation is at 2. So both of them have the same mean, but different standard deviation. So you can see their mean is all going to be in the center of our graph, but then look at how spread out the curve in the blue is compared to the one in the brown. And that's because, you know, it has a standard deviation of 2. That's telling us it's going to be a little bit more spread out. It's going to be a little bit more dispersed, if you will. Okay, so having the same mean but different standard deviation, you can kind of see what this graph on the left-hand side looks like. However, if you have, let's say, a curve that has a mean at 0 and a standard deviation of 2, and you have another curve that has a mean at 2 and standard deviation of 2. So in this case, you will notice they have the same standard deviation, but they have different means. So look at the graph on the right-hand side, graph B. They both have the same shape because, you know, their dispersion, standard deviation is the same value, but because the mean is in 2 different locations, you can see how this mu equals 2 graph has basically moved 2 units to the right. So just a comparison, when you have the same standard deviation and different means, or you have the same mean with 2 different standard deviation, how different those curves will end up looking like. So just as we are working through these normal distribution graphs, remember the curve will be bell-shaped. In these kind of distributions, your mean, median, and mode are all going to be the same value, and of course they will all be located at the center of the distribution. So right in the middle where you have your mean, you also have the mode and the median in that location. So you can see right here in the center is where your mean, median, and mode are going to be. Of course, our normal distribution curves are unimodal, and we had seen this back, you know, when we first talked about the different shapes of our distributions, which basically means it has only one mode. So of course, your mode again is going to be right at that center where your mu or mean value is going to be at. Symmetry is going to be a big part of these normal distribution curves. And remember, that's going to make our calculations